Excellent, thanks. I guess I coined this phrase from, I think that I heard this phrase first from Greg Hall, who used to be Chief Exploration Geologist for Placidome and then Barrick for a while. Yeah, he talked about really where we were going in terms of collecting large geochemical data sets and how it was really starting to become the new geophysics in exploration. I guess just to air a bit more dirty laundry, so yes, I'm a geochemist, yes, I am a POM, and yes, I did change my allegiance on cricket teams at about the time that Australia stopped playing cricket well. So here's the problem. So this is the challenge that we face as an industry. There's a perception out there that as you drive down the road somewhere in the middle of WA, is that someone said it, now the gold's gone, mate, go home, walk away. And then you can see the kind of landscape we're dealing with, and it's really a challenge of is that really the case, or do we actually just have to use some new techniques, some new thinking to go and explore some more?
Or just tell me that could be POM.
The POM thing does account for a fair bit. And here's the challenge. Here's the real challenge that we face, I think, in the fact that we're trying to locate what is essentially quite a small target in a set of complicated basement geology, overlain by a set of quite complicated basin stratigraphy and weathering and regolith, overlain by, in large parts of places like WA, overlain by these horrible sheet wash gravels that I think someone talked about, 10 metres being deep cover in effect. Actually, some of those sheet wash gravels, if they're a couple of metres or 1.5 metres thick, you won't see a signal of the underlying geology through them. So it doesn't take much to hide that geology. And this is a real challenge for us. And of course, those cover sequences can be complicated in their own right. And of course, you always hear the terms basement and cover. And of course, basement and cover means different things to different people, and depending on where you're kind of sitting in the geology. And probably one of the things we do need to think about a little bit as well is that actually some of those cover sequences actually could potentially contain some quite prospective ground, particularly where you're recycling, say, for instance, copper out of original ASEGs and depositing it as SEDEX copper in the basins. Something we should not forget about. So yeah, we get quite complicated cover, and the thicknesses are quite variable. The processes of moving metals, if you like, through the cover sequences are different in different places, and sometimes they're completely blind. One of the things that I guess we've all started to think about is this concept of mineral systems. You've heard it a lot today. It's really becoming part of the vernacular, and really this was some I guess what we called some questions that were raised, which is really, this is an Andy Barnicoat slide, which was really about sort of starting to frame the thinking around what is a mineral system, or where do we go and look for that deposit within that mineral system in a range of questions. And it was about asking questions on the geodynamics, on the architecture, what are the fluid reservoirs, what are the flow drivers and pathways, what are the deposition mechanisms. And that's where we got to a few years ago. I kind of added in a sixth question, which I think is an important one. It's whether the deposit is preserved, the preservation processes, very important to think about. And it's really just a way of saying, actually, if we can consider all of those aspects, and there's a scale thing as well as a process thing there, if we can consider all of those aspects, it helps us to frame where we go and look next. And, I guess we've heard a little bit about this as well. We've heard the notion or the term footprints a fair bit. This, again, is something that's becoming quite widely used. Really talking about moving the industry away from direct detection of the ore body to being able to detect the halo or something that's more distal to the ore body and know you're in a system. It's really about that confidence of saying, tick, yes, we're in a system. Now we can focus on where we need to go. And having the confidence to say you're in the right system or a system that's going to give you something prospective. And this is just a picture as an example of some work we did at Ranger. So this is the uranium system, where you've got a series of kind of quite well-defined mineralogical halos around that system that really extend the system itself by several kilometres. And actually, what we found was that there's a particular type of alteration up in the Cambodia sandstone that is a very, very distinctive signal of the presence of underlying uranium ore, but does not in its own right contain any uranium whatsoever. But you actually have to understand the whole system and what's going on with the chemistry, what's going on in the mineralogy there, to really know that seeing the signal of that as you're drilling tells you there's something here. So that's the kind of the distal footprints take on this whole thing. And the problem is, I guess, is that those distal footprints can be quite broad and all the rest of it, but we don't have much to go on. That's the drill core. So we might be drilling something that maybe has a kilometre footprint, but we're only sampling with this kind of, whatever, 10 centimetre, 5 centimetre stick of rock. So there's a real challenge as well for the geochemists and the mineralogists of how do you go and collect the kind of data you need to collect and extrapolate it into that volume based on the fact that you're only getting that little bit of core there. And one of the things I've certainly started to refer to these things as sample recovery units rather than drill rigs, because that's actually what they're designed to do. It's not about drilling the core, it's about actually recovering the sample. And that drilling process itself, one of the other challenges we face, of course, is that's a really slow process. To go from drilling and sampling and measuring that core, interpreting the data you get back, and of course, the measuring to interpreting thing can be 3 to 6 months. And then taking that interpretation and making a target and then re-drilling it, that whole cycle, I mean, that easily can take a year in some cases. And so, of course, the drill rig's been completely demobilised and moved off by the time you've got to the point where you've even got some data coming back in the door. So one of the real challenges we face is reducing the time to move around that drill cycle, and that's really where we're going to see things like sensing hardware and hardware technology evolution starting to have an impact back into here, and that's things like the role of the deep exploration technology CRC in causing that or making that step change. So what is the anatomy of a mineral system and how do we read its story? I just wanted to put this up because, I guess this is something that causes a fair bit of confusion in a range of places. And so I put this picture up again, which again, like I said, is an ore body. We've got a set of stratigraphy, lithological units. There's a set of mineralogical and chemical halos around this. There's some structure in there. And, what you're really looking at there is a combination of lithology. So that's the original rock type there. That's been affected by metamorphism. Gradients in the metamorphism will have quite large distance scales, so several tens of kilometres normally. You then get metasomatism, which comes down to that next scale, which is really your alteration halos, and then your structure over superimposed on that controls where a lot of this is distributed. And I think one of the things I often see, particularly when I'm kind of thinking about geophysical data sets, is we often hear people talk about, we're going to use the geophysics to tell us about the geology, and they talk about the rock units. But actually all of these components will influence the petrophysical response of those rocks. And so actually starting to try and tease apart the geophysical data sets to tell us separately about lithology, metamorphism, metasomatism and structure be a really useful thing for us all to think about how to do that. And I think the key is going to be, and what I hope to get to in this talk, I think the key is going to be interfacing the geochemistry, mineralogy back in with the petrophysics. This was a picture that's been doing the rounds a fair bit. It's probably one of those data sets that potentially was not meant to ever get out, but has gone out widely to the whole community. This is actually a beautiful data set. You can see the scale bar there. This is top of fresh rock. So this is just RAB drilling down to top of fresh rock, down to resistance, and taking a sample and then just running it through a 4-acid digest ICP-MS to get 60 chemical elements. And this is some data that Scott Halley basically compiled his time with Placer. And what you're looking at there is a part of the goldfields of Western Australia, so the Golden Miles here, Canowna Bell, Paddington. And what you can see there straight away from that data set is that we're getting a picture out of chemistry that is very akin to the kind of pictures you would get from a geophysical data set. And what you're starting to see there is patterns related to the underlying fluid flow, metasomatism. This is antimony. And basically what you're seeing here is the pathways, if you like, or the presence of rocks that have been interacted with magmatic fluids in that case. And that's associated with some of the gold story there and how we find gold deposits. But what you can immediately garner from that is that those are really big signals, those are really big footprints. So they're big scale systems, but that actually when you start to collect a data set like that, the pattern of those systems immediately becomes obvious. And it kind of helps to tell you where to go. And that's just looking at one element. But this was really where the notion of geochemistry becoming the new geophysics started to come from, because we're starting to collect these patterns of data. Now there's a fair bit of work in there, but one of the things we hope to get to, of course, is to improve the technology such that we can start to collect these kind of data sets very routinely, very quickly, and very cheaply. Because I think that will really help to garner where we go. One of the other interesting things here is a lot of the white patches. Well, some of that's about tenement boundaries, okay, because this is a placer data set effectively. But some of that as well is about these sheet wash gravels. And some of that's just about the fact that no one ever went there because there was a metre or 5 metres or 10 metres of sheet wash gravels, and it was blind to the surface, so no one ever went to explore. In shallow cover scenarios, I guess, there's been a fair bit of work on geochemical prospecting through shallow cover. And there's a whole bunch of techniques that are kicking around, fair bit of work in the last 10 years in particular, around things we can do to look at that. And so what a lot of that work has done is, again, taking the idea of direct detection of ore bodies, but now looking at how you would do the direct detection through shallow cover, where you're actually transporting the metals from the ore zone up through the cover, and you're getting some kind of signal at surface. There's a whole bunch of bizarre stuff that's been tried, but these are some of the things that have been used. People have been using things like hydrogeochemistry, for instance, looking at the signals in the waters. They've been using things like termite mounds, sampling termite mounds, because the termites bring the material up from a few tens of metres. Some of these trees, the eucalypts and stuff, where their root zones can go down 100 metres, and they're really tapping the rock at 100 metres and then bringing that metal signal up and depositing it in the leaves effectively. You just go around, ash the leaves, analyse them. So there's been a fair bit of work done in these kind of environments, it's kind of shallow environments, but really sort of the 100 metres is about the limit for those kind of techniques. And even then, some of them are a bit sketchy. So really, what I was thinking about was, what kind of things, just as a bit of a summary, what kind of things might we chuck at it if we had different kind of erosional levels in here? And, certainly if the basement or the fresh rock is exposed, you're going to be using whole rock geochemistry. You can use mineralogy. Mineralogy I'll touch on a bit, because it's really something that people have forgotten about, but actually can be routinely collected now. Very useful. Things like mineral chemistry start to be useful in a fresh rock environment, looking at changes in things like mica chemistries, chlorite chemistries. Those things have been shown to be vectors into ore systems. When you're into the in situ regolith, so this is the really weathered, cruddy rocks that people like, people from the UK in particular, bless them, have never seen before in their lives until they go and look at a gold deposit in Western Australia, then you start having to play around with the geochemistry a bit. You have to start using immobile components of the chemistry that don't move around during the weathering. Some of the aspects of the mineralogy, things like resist-state mineral chemistry. So these are the minerals that aren't going to degrade, rutiles, magnetites, and we can start to use those to see through that weathering process. When the cover is less than 50 metres, in the transported cover less than 50 metres, then there's a whole bunch of techniques, and I talked about those. So biogeochem, trees and shrubs, hydrogeochem, gas collectors, all those kind of things. When we start getting into this realm, so the cover thickness being more than 50 to 100 metres, you're really starting to struggle now. So yes, some hydrogeochem techniques can work, but they're quite broad space techniques. They're not very fine scale. And then over and above that, it's really tough. It's really tough. There isn't a lot of techniques that can work from the surface once you're into those environments. So in essence, we have to take a new approach now. One of the things that, I guess, one of the other aspects of geochemistry we're starting to see more uptake on is the kind of when we get into that mine or brownfields environment, is starting to see some quite large geochemical databases built up in those environments that can start to help us to map out aspects of the system that haven't been seen before. And this is just coming back to the example from Ranger. Here's the open pit uranium system in here. This is the one of the horizons, this perspective here with the uranium on it. And this is just sulfur. They happen to, at Ranger, they were routinely collecting multi-element data for every metre and a half, I think, on all the in-mine drilling. I think someone had told them to do it about 12 years ago, and then someone had forgotten to tell them why they were doing it. So when we kind of walked into the mine site, they had this database of 36,000 multi-element analyses that no one had ever looked at. Fantastic for a researcher. But so we started to plot this up in 3D, and the sulfur is really interesting because you can see these kind of vertical structures here. And we actually started to map out architecture in that deposit that related to the fluid flow at the time of mineralization that you couldn't necessarily see even in things like mapped faults and shears and that kind of stuff. So you start to build up a picture of architecture that's really critical at the time of mineralization that you can't see in any other way. And you can get quite complicated with that as well, and we kind of did that, and there's a paper come out just recently on that work. So you can see how in those environments even multi-element geochemistry starts to become quite useful. Of course, what you really want to know, I mean, if you take the rock and you take the core, really all we need to know in some respects is 4 things. So it shouldn't be that hard, really. We just need to know the petrophysical response, we need to know the geochemical response, the mineralogical response, and then some aspect of texture or structure. If you can actually measure all of those or quantify all of those 4 parameters, I can guarantee that you can do pretty well anything you want to do with that data set, be it exploration to geometallurgy to geotechnical studies to anything else, processing. So those are the 4 parameters that we need to garner to kind of to really do things with. One of the approaches that we took about 4 or 5 years ago as part of the PMD CRC, myself and Richard Chopping sat down together. It was probably over beer. And I'm a geochemist and he's a geophysicist, and we kind of sat there and we were I was playing around at the time with reactive transport geochemical models of mineral systems. And what we realised was that I was producing these models that had beautiful distributions of minerals in them. And Richard was sitting there going, well, why don't we just use that to calculate the petrophysical properties and understand what your models would look like in a geophysical sense. And this is a really neat kind of bit of work. And it does touch a little bit on what we were talking about earlier with the seam idea. So here's a model. This is geochemist's view of the world of how gold deposits form. Felsic volcanics, there's a granite, there's a fault, and there's some greenstones. It's very simplified. And you can run the model, and you run it as a reactive transport model, so you populate the fluids, you populate the chemistries into those rock units. It decides what reactions are going to happen as the fluids move around the model. And so you basically end up with a result, a model that is populated with mineralogy. Here's calcite, so the ore deposit forms in here. Here's a calcite plume sitting above and in the ore deposit, basically because of the hot CO2-rich fluids coming off the granite here. Here's a picture of chlorite chemistry, for instance, as it's predicted in this model. And so what we then did was use that on here's just an example of the time evolution of that mineralogy at a particular point. So you've basically got spatial plus a time dimension here as well. And you can see that we can pull out a whole range of minerals. And what Richard did then was to take the mineralogy as recorded at each point in the model and use the mineral thermodynamics in first principles to calculate the petrophysical response of that rock. And there are issues around obviously things like understanding what porosity would do here, but actually the bottom line is this is crystalline rock. The porosity is really small. It doesn't really contribute a lot here, unlike the petroleum systems. One of the big differences. And so what Richard did was then to take, so here's just an image of density, for instance, and here's the calculated density at the end of that model there. And you can see, and what he's done then is to put an erosion surface in and say, what if this was exposed at this level? And you can see the reduction in density here due to the presence of carbonate alteration in that greenstone environment. So what we're seeing here now is a modelled gravity response where the gravity response is low, not because of lithology, not because of the geology itself, but because of the carbonate alteration, the carbonate pipes. And this actually led to some rethinking about even some of the geophysical signals we were seeing around the gold deposits, where people were interpreting some things as porphyry intrusions and those kind of things. And we were saying, well, actually, maybe this is about carbonate alteration. So I think it's a really important aspect here. And I'm really keen to kind of explore this when we think about synthetic models, because what we can do, of course, is build synthetic models that just have a distribution of mineralogy. And then you're not predisposing the petrophysical responses, you're just using the distribution of mineralogy, which we know quite well in most systems, to calculate the petrophysical response of those synthetic models. So I think that might be kind of a neat approach. And you can see that you can play a bunch of games, deposit buried at different depths, deposit crops out, deposit is eroded. So it really was a first pass attempt at some of this synthetic modelling that we talked about earlier. And it's one I'd like to kind of cover a bit, maybe in the discussion. But technology really is driving the way forward here. I mean, you know, the problem with geochemistry and mineralogy has been that it's blooming expensive to collect the data. There's no two ways about it. If you go to a lab and you do a 4-acid digest ICP-MS finish for 60 elements, it's going to cost you, well, if you're doing it routinely, maybe $50, but maybe $110 if you're not doing it routinely. That's a fair cost outlay to collect that information routinely, and there's a massive time delay. But the technology really is kind of pushing us, right? So what I'm doing today is I'm standing up and giving you the vision, and then we'll just rely on a bunch of people to make it happen, right? that happens a fair bit. Can't be hard. Because the issue, I guess, is illustrated in these next two slides for geochemistry. So this is geochemical prospecting in 1850. This is some pictures from Southern Cross, I believe. And you can see that you've got a pan there. They've been panning out some gold nuggets there, but basically panning out some heavy separates and wandering around looking in streams and stuff. And this is geochemical prospecting in 2012. There's a bunch of people with some pans wandering around collecting stuff in streams. That's a bit poor, isn't it? We haven't evolved. We haven't evolved. So maybe worse, yeah, if we don't do it. So we've certainly got to a point where around things like geochemistry, geochemical prospecting, and those kind of things, is that we haven't taken advantage of where the technology's got. And I think what was really nice was so Tim Monday. I was talking to Tim about this, and he said, "Well, here's the story of the airborne EM." And it's this notion of technology evolution and how it impacts. And I presume these slides came from someone quite eminent. But
reliable.
Reliable. And talking about the kind of the application of airborne EM and looking at those kind of discovery rates and how it impacted. And the one I quite liked, I probably misinterpreted it, but anyway, was how kind of the technology application changes into different deposits here, or changes the type of technology platform, such that you get bursts of discoveries in these different applications. And that's really nice, seeing how the platform's moved into different applications. And this notion of a platform is something that's been around in geophysics space, but hasn't really come into the kind of geochemical space so much. And so this kind of notion of this kind of multi-sensor platform buzzing around, collecting all those data sets. And, so in geochemistry space, we've come up with techniques. So there are techniques like, say, for instance, calcrete sampling. Someone mentioned Tropicana earlier, right? So Tropicana was found because of an anomaly, a gold anomaly in a calcrete sample, because WMC at the time had just peppered the whole Albany Fraser with calcrete samples, because this technique had been developed, which showed that it worked well for a bunch of systems. But we haven't really driven that out there in terms of a platform that you can roll out. And so, I guess where we're starting to think now is that what we have in geochemical sense is, and actually in the petrophysical sense, is we now start to think about the platform, the technology platform here being the drill rig. So the drill rig's always been a means to an end, i.e. you're just going to go and drill a hole and collect a piece of core. But actually I want you to start thinking about this as a technology platform we're kind of terming it the regional explorer, the regional prospecting rig. But really starting to think about this as a technology platform that's going to go out there and do the prospecting. And then we need to bolt the technology in to allow us to collect all those data sets that we've previously been looking at. And really what that's about, and I guess where we're coming to that whole notion with is starting to really bring into unlocking that technology, really bringing kind of research together with the service sector and the people like the government and surveys in Australia to kind of unlock that mining and exploration sector here. And it's about getting those people working together for the end users, because you're going to work with the service sector because you want the stuff out there as a commercial product. You don't want it to sit on the bookshelves. I think that comment was talked about. So you partner very early, and you partner with these guys because they're out there generating the pre-competitive data set to unlock the value for the end user. And that's the approach we're really taking in things like the DET CRC. One of the big developments, I guess, that's really impacted in a huge way into geochemistry has been the development of silicon drift detectors. So silicon drift X-ray detectors. So this paper came out in 1984, which was really the paper that talked about the technology, the detector technology. So it's taken that long to kind of really mature. But these silicon drift detectors have allowed us to produce high X-ray counts. They're high energy resolution. You can Peltier cool. You don't need to walk around with liquid nitrogen. And what that's done is it's just opened up a whole new space of the application of X-ray measuring in things like portable XRF, for instance, as a technology that now is routinely seen out in industry. And so a development like that, even though there's a long lead in time, can open up geochemistry in this case to being rapid, achievable, accessible at very low cost. And of course, what we've also got out there at the moment, in a very different search space, is a technology prototype that's running around with a whole bunch of devices on it that are really, really interesting for us in mineral sector. There's a whole bunch of technology sat on the Curiosity rover up on Mars at the moment that is really, really going to be really useful for us in the long run. So it's a really great prototype to go and look at. I suggest you go and look at the website, have a look at what it's doing. But needless to say, the CheMin system, this system here, which is a coupled XRF XRD system, it's a box that sits in here. You can actually go and purchase a version of that box. It's called the Terra Portable XRD system, and you can go and use that right now. So that technology is already flowing through to our markets. But there's a bunch of other stuff on here. APSX, the SAM is a little ICP system that sits on the Curiosity. ChemCam is a LIB system, so laser-induced breakdown spectroscopy. They're allowed to fire their laser across 25 meters. I don't think we're going to get away with that on Earth. But certainly, you basically blast the rock with a laser and measure the fluorescence spectra of the plasma. So there's a whole bunch of really neat technology there. One of the beauties of the NASA model, I guess, in some respects as well, is that they put patents onto things and that kind of stuff, but that technology basically has got out there, pushed out there with the service sector quite quickly. So we've got access to this, and we're kind of looking at this as a prototype of some of the places we want to go with our new technologies. So here's an example of the CheMin as applied to mineral exploration. So the CheMin is a portable XRD system. Basically a CCD with an X-ray tube, put your sample in the middle there, and you get a diffraction pattern. You basically got a diffraction pattern coupled with an XRF system. This is what it looks like here. This is a desktop portable XRF system, or what they call portable XRF system here. And this is, like I say, technology that came out of developing it for the Curiosity program that's now kind of starting to make its way into our sector. The XRD, I think, is what's going to become a real kind of game changer for a lot of what we do, because one of the things we don't do routinely is measure mineralogy. And suddenly we've got some technology, plus we need a bit of smarts in the processing to produce routine mineralogy. Processing is probably the biggest challenge, actually. The hardware in some respects has got to a point now where it's way beyond the capabilities of the processing algorithms to keep up. A lot of what we're using at the moment, say in the portable XRF environment, are processing algorithms that are about 12, 15 years old. So there's a fair fair opportunity and challenge around actually being able to process the wiggly lines. It's all about wiggly lines, I've learned that. So processing and the kind of software to process and present to the geologist or the exploration geologist information, not just a wiggly line, is probably one of the challenges we need to work on as a community. And so really what we're talking about here is in things like the deep exploration technologies, CRC, we're really talking about kind of developing technologies around things like developing technologies around the drill rig, around the sensing while drilling, and around applications like lab at rig with these kind of technologies to bring those all together to help decision support. So you can generate data sets like this and know where you're going to go, and you can do it in a time frame and at a cost effectiveness that means that we can go and prospect with drilling like we used to with a pan and a shovel downstreams. And really where we're going to is starting to produce data like this in the geochemical mineralogical space, data like this while we're drilling. So you've got things that here's chemistry, iron and sulfur here, you've got mineralogy, which is pyrite, pyrrhotite, abundance, logs. Here we've got MagSus as a downhole plot. But as geochemists and mineralogists, we've never had data like that to play with. The geophysicists have at least had downhole petrophysics information in the most part, but we've never had data like this. And now we're going to be at a point in the next kind of couple of years at least that we're going to be routinely having technology available to produce these kind of data sets. It's going to revolutionise what we can start to do, I believe. What it all needs to come back to at the end of the day is that we need to be able to take this data and do stuff with it. So there's no point in just producing the data, but we need to actually turn it into information or knowledge, and in particular we need to put it into an environment where we can understand what's going on as we're drilling in our 3D geological environment. And so there's a fair bit of work that needs to be done also around the big data issue. And again, that's something that geophysicists have grappled with for a fair bit of time. It's something that geochemists and mineralogists and co have just started to get to the point where we're going to be starting to collect data at the same quantity. We're going to have to deal with the same issue. So dealing with big data is a challenge, but that's something that I can see that the community is starting to deal with. So I just wanted to kind of, I guess, get towards the back end with a bit of a window on the future of where I can see people like myself working with the geophysical community in the future, and maybe some of the opportunities that opens up. I got this picture, I gratuitously stole this from a slide I think that Tim and Dave Gray had kind of cobbled together at some point, and it's a really neat example of, I think, the kind of opportunities that are afforded to us now. This is soil samples here of copper, and if you remember back to some of the first few slides I showed, I talked about the fact that in certain environments, yes, you can use soil data, copper, to tell you what's underneath. In certain other environments, it becomes a bit harder, and when the cover thickness is beyond a certain amount, you forget it, walk away. And so what this is soil copper data with an underlying AEM map in essence of the cover thickness or the complexity of that regolith characterisation. And so you can immediately see the opportunity there in terms of being able to filter that data set for what is useless versus what means something, or even be able to normalise your copper data, for instance, to the distance from the basement or the process that got the copper there. Is it direct sampling? Is it been transported by fluids? Is it just blind? Of course, ultimately what we should be doing, of course, is running the AEM first, and then knowing we don't even go and take samples in the deep cover areas, not soil samples. But what we do is we go and take soil samples in the shallow cover areas and get our regional prospecting drill rig in to drill to the basement interface in the deep areas. So understanding using things like the AEM there, for instance, to produce a map that tells us what techniques we want to go and use in different places. So those are really going to be really useful products in the future. And there's just an example again of chrome. And again, you can see in this map here that there's a whole bunch of blues there, and it's about the fact that those areas are covered. The data point there does not represent the rock underneath because it's blind to it. So if this is actually a survey GSWA data set, but in some respects you're not going to go and sample here to tell you about the underlying geology. That's for sure. So knowing that by running your geophysical survey first is a really useful exercise. Because, you know, we can start to characterize these cross sections like this. This is another gratuitous Tim Monday effort, I think. We can start to characterize that cover with these geophysical techniques that really tell us what geochemical processes are operating at what places here: outcrop, subcrop, deep cover. Okay, so we need to be working more closely together. That's just one example. Of course, the integration into 3D of the geophysics with the geology and the geochemistry is going to be critical. And this was something I did in Leapfrog about 5 years ago. And the company had multiple data sets lying around on databases, and people like me get in there and start pulling stuff left, right and centre, chucking it into a 3D platform. And they just hadn't done this exercise before. They hadn't ever looked at the lithological model with the gold deposit in 3D versus the kind of petrophysical, or the kind of geophysical data sets they'd gone and collected. You know, this was the realm of the geophysicist and this was the realm of the geologist. They'd never put the two together. And so just a simple exercise of just visualizing the data sets together was enough to drive a whole conversation around what it really meant that hadn't happened before. So I think we need to be more seamless about the way we're putting these data sets together in a true way. And of course the feedback will be that it will help us to better constrain maybe the kinds of inversions we do, or the kind of inversions that we know are working. That's to help to kind of feed that back. We can get quite tricky if we're going to start going and collecting really routine geochemistry. We can start to get quite fancy with the kind of analytics we do. Geophysicists do some pretty fancy analytics. Geochemists don't normally, but actually we can start to go and do fancy stuff. This is an example of a nuggety gold deposit. What we're doing here is moving away from just producing isosurfaces of the gold only to actually producing isosurfaces of probability of finding gold based on a whole set of criteria. Things like the structure, things like the alteration, the mineralogy, the geochemical signal, multi-element geochemical signal. What I'd like to have in there, of course, is the petrophysical response as well. And we bring all those aspects in and produce a probability shell. And you can see that, it's hard to see because of the colours, but you can see that the continuity there, this is a cross-section, continuity, you see a steep structure here. You couldn't see any of that patterning in the gold itself. This is a real revolution for the company. But it's possible because we're now, A, collecting the data more routinely because we've got the technology to do it. B, we're bringing the data sets together and we're doing that because we want to run analytics to do this kind of stuff. So this is a really neat example of being able to do that. And get really, really fancy, and even I kind of struggle with this a bit, but this is, and you guys will be familiar with this technique, this is a wavelet technique, basically an edge detection technique, where we're looking at different scales, from the scale of a sulfide vein to the scale of a big, broad sulfide zone, down a single drill hole where we've collected this kind of XRF type chemistry. And what we're doing is starting to have a look at algorithms or analytics for doing domaining, so automated domaining, where different scales might relate to either broad rock types or it might relate to the kind of sulfide veins and that kind of stuff. So again, now that we're starting to collect the data routinely, we can start to approach it in the way that geophysicists have in terms of starting to do stuff, because your data density is such that you can start to apply these kind of analytics. So there's a lot we can learn from this community about how we can do this stuff, and we can provide a fair bit of information back to you as well about the petrophysical responses. So that's good. It leaves plenty of time for discussion, which is what I hoped. So there's a few kind of points. I mean, the reality is we're moving into a brave new world where we can produce, or we will be producing, lab quality, real-time geochemistry and mineralogy while drilling. That just hasn't been done before routinely. We'll now have the technology to do that, and it will start to be utilised more and more and more. Those data sets are going to become available. So it'll be like geochemistry and mineralogy, like a wireline log. We've just, as a community, as a geochemist, I've never seen that kind of data set before, but we're going to get there now. certainly one of the big drivers for us is trying to move in the technology space, move away from single sensors to coupled sensors. So I talked about the CheMin system, which is a coupled XRF XRD, so chemistry and mineralogy. I think coupled sensors are really, really critical. It's going to be a really critical way forward, because if you can start to, in real time, couple, say, your, in our sense, an XRF spectrum with an XRD spectrum, you can actually start to do inversion between those two data sets to give you a much better control on the output. If we're collecting petrophysical information at the same time, if we're collecting, you know, the downhole gamma, the downhole whatever else, and we're bringing it all together, the opportunity is going to be huge to bring all those data streams together into one place and run the analytics on everything, regardless of what it is. I think that's going to be a great game changer for the industry down the track. And so the data platform analytics becomes quite a strong underpinning for all of this, to actually mean that we're not just producing data for the sake of data, but we're turning that data into information that's going to support decision making in exploration targeting. And that's a really critical aspect to all of this. So this talk has a whole bunch of ideas and contributions. I just thought I'd better chuck up a bunch of names there, because, you know, there's a whole bunch of people who have contributed variable amounts of ideas into this. So that's really useful, and I might just leave it there and maybe drive some discussion around this. So thanks very much.
Thanks, James. That was great. Questions for James? Oh. Smith.
James, one of our great geophysical innovators, Tony Barringer, put his mind to geochemistry in aircraft. Is the sampling of aerosols in a plane a hopeless case, it'll never happen, or is there any work being done?
Well, I mean, there's a whole bunch of techniques out there for aerosol sampling in aircraft that I'm aware of. It's not an area of my expertise around things like volcano monitoring and that kind of stuff. Yeah, I'm not sure I'd understand the application into the mineral sector, that's for sure. I think, yeah, it's not a field of expertise of mine.
James, I've seen a couple of really astounding examples of, like you mentioned, you know, the geometallurgy sphere and rock properties for,
yep,
you know, the mill, like grinding, yep, factor and stuff like that, coming out of 60 multi-element geochem. And so when I've seen this, I've then become quite despondent about, you know, what are we going to do with resistivity, mag sus density, and you know, what do you see as still the spheres where the actual petrophysics is going to still have some kind of competitive or some edge that the geochem doesn't?
I mean, yeah, that's good. That is a good question, because you know, I think there's a question we need to ask ourselves about how much, if you can fully quantify the mineralogy and the full geochemistry of a rock, how much does the petrophysical measurement contribute versus what you can calculate? And that's something I guess I've grappled with a little bit. I think one of the things is that the geochemistry and the mineralogy are recorded as point data that have a very limited sphere of influence away from the observable point. And I still believe that things like downhole petrophysics obviously are they're kind of sampling a bigger volume. But ultimately, really, I guess what we need to be using the geophysics and the petrophysics is the link, is to use the geophysics to extrapolate the geochemistry and mineralogy away from that 1D stick of core or hole into the broader volume. But yeah, I mean, you know, I guess I've touched on the petrophysics aspect with the work, a little bit of work I did with Richard Chopping. I'm really keen to hear from this audience exactly that. It's, you know, if we could fully characterise mineralogy and geochemistry, what aspects can't we calculate that you'd still need to measure, or do you actually render petrophysical measurements or some petrophysical measurements meaningless? It's a good question.
I was interested to hear you say that because that's what I was going to ask about. I mean, I can see you forward modelling bulk properties like density and velocity,
Yep.
but you're going to need to forward model the textures, for example, to predict electrical responses.
Yeah.
To what extent can you do that kind of thing?
Well, I think so the kind of the little bit of the elephant in the room in some respects is that fourth property I talked about, which is texture. And I guess we're not doing a whole heap around being able to automatically measure texture down holes and stuff. There's a bunch of commercial systems out there that kind of try and do it. But it's a good point about how you meld your geochemical information with textual information, or what scale that needs to be at to be able to start to calculate some of those kind of properties. And of course, the obvious one being, conductivity. How do you capture the textual information of the sulfide connectivity to tell you about conductivity versus resistivity without just using a bulk sulfur property? Texture's probably a really hairy one, and I think people kind of felt a little bit that it had been dealt with, and there's commercial televiewer systems and all the rest of it out there, but I'm not sure that potentially we're doing it at the right scale or magnitude that we need to be. So it's a really important one that we probably need to address as a community.
Guys in the corner are awake.
I just might add to that little bit of discussion there, and I think that just thinking about the oil industry is perhaps worthwhile here, because texture is absolutely vital in terms of mineralogy for the oil industry. You want to know what the morphology of clay minerals is because of its impact on porosity and permeability, and I don't think that they do that remotely. I think they do that typically with actually SEM analysis of chip samples or whatever. So
Yep.
It's quite possible that the challenge that Mike puts up there is actually one that is currently insuperable. Not to say that it always will be, and it's undoubtedly a different problem when you're dealing with conductivity, but I think it is worth just facing the fact that we may not be going to get there in the next little while, without wishing to put a downer on it.
Yeah, and I guess one of the other aspects to bear in mind, I think, as well in all of this is, I guess my sense is that for greenfields exploration, or the exploration domain, we're moving to a world of coreless drilling. Okay, we're not going to recover a solid core sample. We're going to be recovering other types of samples. If we go to routine use of core tube drilling, it's going to be a rock flour or powder and dealing with that. But I think that when you move into that brownfields environment, in particular, having some amount of core and being able to deal with the textural context. And for people that know me, I'm a great advocate of advanced characterisation, and I play around with SEMs and XRF mappers and all this kind of stuff. And I think there's a domain difference between the kind of exploration bit of the industry and moving into that kind of resource drill out, where we'll have to retain a sample for exactly that purpose, the kind of textual context of all of that information.
Got a question, Charles?
Yeah, James, in the exploration environment, still the big cost step is going to the drill hole, and it was a really good example of the geochemistry to devise petrophysical properties. But because you can remotely detect petrophysical properties, maybe the big step change is in deriving whole rock chemistry from the petrophysics as opposed to going the other way around.
Yeah, I mean, you could. I think, yeah. And we've played around with it. I mean, I think and you could certainly make a stab at using the petrophysics to tell you about the major element chemistry and that kind of stuff. But you're never going to use it to tell you about the trace element chemistry. That real-time data I talked about is the technology that we're developing in things like the DET CRC is going to mean that we're going to be producing geochemistry at exactly the same rate and exactly the same similar method to that you're producing downhole petrophysics now. So the technology is going to get us there anyway, in some respects.
I may be a simple geologist, but I think that the power is in the combination of the geology and the geochemistry and the geophysics. So it's texture is not too difficult to find out when you look at the rock visually. So you can use a geologist for that. It's pretty simple. While he's taking his geochemical or geophysical measurement, and geochem doesn't differentiate between magnetite and hematite. I don't think all that well. But
the XRD will.
But the your mag sus certainly will. So I think it's,
Yeah,
it's the combination of the three methodologies,
Yep.
and try not to do everything with any single one. It's not a competition; it's a team game.
Yeah.
That's going to give us
Yep.
the quick answers, and what you need is going to vary from project to project, and
Yep.
you have to adapt those. But having a little curiosity machine that can go down the drill hole might be quite neat. But I suspect you're still going to be looking at the drill core for some time, so you can use the combination to get the right answers, I think.
Yep. Yep.
For 500 million, you can have your own curiosity.
It's the nuclear reactor that's the problem.
Back wall is alive and well too. It's good.
Hi, thanks for your talks. Very good. Just about petrophysics, I know that we have anisotropy and orientation, so I mean that's one factor. I wanted to ask you though, downhole I'm a geophysicist, deal a lot with magnetics.
Yep.
In Tennant Creek, a long time ago, talking 60s, they were putting downhole magnetometers down to great effect. And then these tools have been around to be able to put down drill holes for a long time. I can't get any of my clients to put any tools down drill holes, so I don't know why they start, just because new tools become available. And secondly, I loved what you said about aerial coverage of geochemistry and limiting it to where it's going to have great effect. I feel the same way about air magnetics. Would you like to see the same number of samples taken over that more prospective area, or do you think, is data density important?
Data density is really critical, and I guess one of the things that you see when you go and open up a regional soil survey like that GSWA data set is that when you really start to burrow into it, you realise that there's plenty of places where they could have not taken as many samples or even not taken samples. I guess what it's about, of course, is being able to have the data available in real time so that you can make those calls on the fly, which is probably where we need to get to. So there they go and take a bunch of samples and send it away to the lab, and data comes back in 6 months. Oh, didn't need to take all those. Well, didn't know. But actually, if you know right there and then, you're building that picture up as you go, then you can absolutely be very dynamic about.
If you are properly,
Yep.
combining techniques, should you know
Yeah.
already?
Well, and I guess certainly that was the point I was trying to make about just something simple like airborne EM. It's like go and fly the airborne EM and understand what technique you need to use where. Because immediately using the geophysics to give you a kind of a map of exploration technique, I guess. Yeah.
One thing, there's a question in the back, I'll get to it, but I wanted to say it's interesting when I heard about the tube drilling, as my mind works. Anyways, he reminded me of the development of the 117 stealth bomber, or stealth fighter. And of course, in the beginning, an Air Force guy thought it'd be great to have an invisible airplane. But then somebody actually said, what do we do with an invisible airplane? Do we pirouette around the enemy and not get shot? And it was actually the guy who gets, I think, the most kudos is the guy who developed the laser-guided bomb. Because ultimately, that's why the stealth plane was effective. Was you could get to a high-value target, and you could basically, as they said when they went to Baghdad in '91, put it into a command and control center and leave the orphanage on the other side of the street alone. Very, very effective. And I think what James is describing here is the laser-guided bomb for me. The stealth plane might be Richard's tube drilling machine, but you need the adjunct technologies to make it really effective, the solution. But there's one other aspect, and Richard may have the slide again, he showed it in Vancouver. But you generate all this data at the dog box, right? And he had a little like DirecTV antenna, and it shot up, went through the sky, and it landed on this television monitor, and this sort of 20-something boy and girl were standing there looking at the screen. I thought, yeah, they're going to be interpreting terabytes of data right now, okay? And there's a real sociological implication as to what we do with all this information. Because Schlumberger currently has those boxes on drill rigs in the Gulf of Mexico and in the North Sea and all the rest of it, generating those terabytes of data. But they have really well-paid, lots of log engineers to basically analyze that.
Yep.
And that's something which I would implore you to think about. It's not just the generation of data. We need knowledge, we need guidance, and it probably has to be almost in real time.
Yep.
We have to be able to turn this around. People say that, But I haven't quite seen the component of the story that suggests we're going to be able to cope with all of that information. So guys like you, Des and John, I implore you guys to think about that, because you're the clever people in that space to do that sort of data. No, I got a guy in the back. I got a service. Oh, sorry.
Couldn't have happened to a better person.
It's worth paying the money to get serviced by Ken. I just wanted to comment on Matt's comment about, I agree with him, I don't think by developing new tools, you're not going to suddenly do lots of wireline deployments. The key is the technology that permits a different deployment. So the sensors that James is talking about, and the sensors we're developing, can be deployed either on conventional diamond coring, just as you core, or else they will sit on a sub behind the bit. And so all of this data will be acquired by the driller, and what is the quantum lead is the extra data at almost no extra cost. These tools aren't going to go down on a wireline. You lose the holes and you have to mobilize a separate crew.
Okay, Kim. And Kim will be the last one. We will get, as you hope, James, we've got some good questions.
Just a quick comment, and picking up on that comment you made about your clients not running downhole mag. They're doing it all the time. Every time they run a multi-shot, they've got a 3-component mag survey. All you need to do is reprocess it.
Downhole by stealth. All right, thanks, James. Oh, geez, Jesse, you're scratching your head.
Yeah, I was, mate. I mean, James has sort of nailed the problem, though, in that, the drill hole and the whole business of how the hell are we going to develop a multi-scale way of coping, because you write down like an ant's view of the geology, and the dynamic 3D model, that's in a completely different space and a different scale. We have no idea how the hell to do that.
Fair enough.
All right.